This is the first lecture for Module 4 of MAT201 Partial Differential Equations and Complex Analysis. In this module, we will look at integration of complex functions. As in the real case, for complex functions also, we have definite and indefinite integrals. An indefinite integral is a function whose derivative equals a given analytic function. For example, integral of cos z dz equal to sin z. But complex definite integrals are line integrals. They are denoted by integral over c f of z dz. F of z is integrated over a given curve c or a portion of this curve. This curve c is called the path of integration. Complex line integrals have some basic properties. Those are linearity. Then for complex integrals also, if we reverse the sense of integration while integrating over the same path, a minus sign will be introduced. Finally, partitioning of path. If the path of integration c can be partitioned into two paths, c1 and c2, then integral over c f of z dz is integral over c1 f of z dz plus integral over c2 f of z dz. The first evaluation method for complex integrals is applicable only for analytic functions. In this method, we will do an indefinite integration followed by substitution of limits. So for example, integral 0 to 1 plus I z square dz, the indefinite integral of z square is z cube by 3. Once we get the indefinite integral, we can substitute the limits and get the final value of the integral as minus 2 by 3 plus 2 by 3 I. Similarly, integral of cos z is sin z. So integral minus pi I to plus pi I cos z dz is just sin z with the lower limit minus pi I and upper limit pi I. That's 2 times sine of pi I. The second evaluation method is a more general method. This method can be applied for any continuous complex function, not just analytic functions. But this method will use the representation of the path of integration. So the steps in second evaluation method are: first, represent the path of integration c in the form z of t equal to x of t plus I y of t, where t is between a and b. Calculate z dash of t. Then substitute z of t for z in f of z. Finally, integrate f of z of t, z dash of t over t from a to b. Then integral over c f of z dz equals integral a to b f of z of t, z dash of t dt. Let's look at some examples. First one, evaluate integral over c real part of z dz, where c is the shortest path from 0 to 1 plus I. The function to be integrated is f of z equal to real part of z. If z equal to x plus iy, then real part of z is just x. That's the function which we have to integrate. The path of integration is the shortest path from 0 to 1 plus I. That is the segment of the line y equal to x from the origin 0, 0 to the point 1, 1. From this, we get the required parametric representation of the curve C. Z is equal to x of t plus iy of t. X is t, then y of t is also t. So the parametric representation is z equal to t plus it with t varying from 0 to 1. So x of t and y of t are both equal to t. A is 0 and b is 1. Z dash of t can be calculated as 1 plus I. F of z of t is just x of t, that's t itself. Finally, we can integrate. Integral over c f of z dz is integral over a to b f of z of t z dash of t dt. Substitute for all the terms. This is integral 0 to 1 t times 1 plus I dt. Integrating as usual, the value of this integral is 1 plus I divided by 2. Let's look at another example. Evaluate integral over c dz by z, where c is the unit circle, that is the circle with radius 1 and center 0, oriented counterclockwise. Here we use polar coordinates. In polar coordinates, a point on the unit circle can be represented as x equal to 1 cos t, y equal to 1 sin t. Then z of t, which is x plus iy, is cos t plus I sin t. If we also apply Euler's formula, z of t is just e raised to it. Now the unit circle is given to be oriented counterclockwise. So as t increases, we should move in a counterclockwise direction along the unit circle. So t should vary from 0 to 2 pi. So we found the parametric representation. Then the next step is evaluating z dash of t. Z of t is e raised to it. If we apply chain rule, z dash of t is I e raised to it. The given function f of z is 1 by z. So again substituting the parametric representation of z, f of z of t is e raised to minus it. Finally, we can calculate the integral. Integral over c f of z dz is integral over a to b f of z of t z dash of t dt. That's integral 0 to 2 pi e raised to minus it I e raised to it dt. The two exponential terms will cancel each other. So finally, we have just I times integral 0 to 2 pi dt. The value of this integral is 2 pi I. We look at another example where we have to integrate over a circle. Evaluate integral over c f of z dz. F of z is z minus z naught raised to m, where m is an integer. Z naught is a complex constant. C is the circle with radius rho and center at z naught. For a circle with radius rho and center at z, the parameterization is z of t equal to z naught plus rho times cos t plus I sin t, that is z naught plus rho e raised to it. Again applying Euler's formula. Here also t varies from 0 to 2 pi. As before, z dash of t is I times rho e raised to it. F of z of t we can find by substituting for z of t, that is rho raised to m e raised to imt. Finally, integral over c f of z dz is integral over 0 to 2 pi rho raised to m e raised to imt times I rho e raised to it dt. If we simplify this expression, this integral equals I times rho raised to m plus 1 integral over 0 to 2 pi e raised to I times m plus 1t dt. Apply Euler's formula once more to the integrand. So our integral will become I times rho raised to m plus 1 integral over 0 to 2 pi cos m plus 1t plus I times sine of m plus 1t dt. To evaluate this integral, we will consider two cases. The first case is when m equals minus 1. If we let m equal to minus 1 in the previous expression, rho raised to m plus 1 will be 1, cos m plus 1t is 1, and sin of m plus 1t is 0. So for this case, the value of the integral will be just 2 pi I. When m is not equal to minus 1, the integral will become I times rho raised to m plus 1 sin m plus 1t by m plus 1 minus I times cos m plus 1t by m plus 1 with limits 0 to 2 pi. But remember that sin and cos are trigonometric functions. They are periodic with period 2 pi. So using this periodicity of trigonometric functions, the value of this integral will become 0. So to conclude, integral over C z minus z0 raised to m dz is 2 pi I when m equal to minus 1, 0 when m is an integer but not equal to minus 1.